Hello all of you. Welcome back to my SB2 channel. We are going to get started on a very new chapter. It's all about the gases and the gas laws. There's going to be an introduction, and then I need to talk about the four gas laws that are pretty common, and they're going to be a practice for you as well at the end. Okay, so starting by our introduction, gases are going to be one of the four main states of matter. And what makes them really special is that they can expand and they can take all the space that is available in the container, and you can also easily compress them. Okay, now there are going to be a bunch of gas laws that we are going to review them on the next few slides. One of the things that is so important for understanding of the gas laws is the pressure and the definition of the pressure. Okay, so the pressure is going to be the force exerted by the gas particles when they are colliding with the walls of the container, right? So the collision between the particles are not going to be matter. When they are actually applying the force on the surface, or let's say the walls of the container, that is how we can define the pressure. Now, keep that in mind, there are many units for the pressure, right? So we have the very common one, which is atmosphere, so that is ATM. We have the mmHg, which is millimeters of the mercury, right? We have kPa, that is your kilopascals. You can also have the PSI, which is the pounds per square inch, okay? When we do the calculations, you're going to see all of these different units depending on the question stem, depending on the practice, right? But just be aware that we have all of these different units for the pressure. Okay, so on this page, we're going to be looking at two of the gas laws, and I have the other two on the next page for you. Okay, so starting by Boyle's law, which is going to be the pressure volume relationship. Okay, so if the temperature of our system is constant, the pressure and the volume are going to be inversely related. What does that mean inversely? That means if one goes up, the other one has to go down. You can also say indirect relationship. The formula that you got to have it in your brain is going to be the P1 V1 that goes to P2 V2. Okay, very common example. If you squeeze a balloon, that means you are decreasing the volume of your balloon. The pressure inside is going to increase, right? Okay, then we have the Charles law, which is the volume temperature relationship. And this is going to be the case that I have a constant pressure, right? And the volume and the temperature are going to be directly proportional. So what does that mean, directly proportional? That means if you increase one of them, the other one has to go up as well. They go up together or down together, right? And the formula is V1 over T1, that goes to V2 over T2. Very cool example is where we have a hot air balloon, right? That is going to always rise because heating the air is going to cause the volume of the balloon to increase, right? Okay, cool. I've got the other two for on the next page. Follow me on the next page, my friends. Okay, so the third one is going to be the Avogadro's law, which is about the volume mole relationship. Okay, so what I have here is I have two of my variables that are the same. So temperature and your pressure are going to be constant, and then the volume is going to be directly proportional to the number of moles of the gas. So what does that mean? That means if you have more moles, like more stuff, they're going to take up bigger space, which is totally makes sense, right? If you're doubling the number of gas particles, you're pretty much doubling the volume of that. And the equation goes by V1 over N1 goes by V2 over N2, okay? Then we have the Guy-Lussac law, which is the pressure-temperature relationship. So in this experiment, right, for this gas law, your volume is constant and your pressure and your temperature are going to be directly proportional. Again, one goes up, the other one has to go up as well. P1 over T1 goes to P2 over T2, right? Cool example is when you're heating a closed aerosol, right? If you have a can of aerosol and you heat that, that means the pressure inside of that is going to increase, okay? Now, take a look at the next page, but I have a really cool practice for you. Okay, so here's the practice. It's quite long, right? So suppose we have a gas confined in a cylinder with a movable piston that is sealed, so we know that there's no leaking for the gas, right? Now, how will each of the following changes affect these three items, which is the pressure, the number of moles of the gas, as well as the average distance between the molecules? Okay, and I have three cases. On the next few slides, we're going to have like one of these, right, at a time. So starting by A on the next page. Okay, so A says heating the gas while maintaining a constant pressure. Okay, so heating the gas means your temperature is going up, right? But you're maintaining your pressure. Okay, it says that we are having a constant pressure, so the pressure has to stay the same, right? Now, the number of moles of the gas is going to also stay the same because we're not adding, we're not removing any gases. And remember, the question stem says that we have no leaking, it's a closed system. Okay, so as a result of that, the average distance between the molecules must increase because heating at constant pressure makes the volume of the gases to expand, and therefore they're going to have bigger space between themselves. Okay, I hope that makes sense. Okay, so for part B, we are looking at reducing the volume while maintaining the constant temperature. So now the volume is going down, but there's no change in your temperature. Okay, so the pressure has to go up. Remember, if you reduce the volume, right, then the pressure has to go up. This is what we got from Boyle's law. In terms of the number of moles of the gas, no change. Again, we did not add, we did not remove any of the gases. Now, if I am reducing the volume, right, that means the average distance between the molecules has to go down because we have the same number of molecules, right, the same number of moles, but now we try to squeeze them. So they're going to have a smaller space between themselves. Okay, cool, cool. Looking at the next one. For part C, it says injecting additional gas while we are trying to keep the temperature and the volume constant. Okay, so the pressure has to go up, right? Because we're adding more moles of the molecules. We have higher number of moles, but we have the same volume. So they're going to be more collisions. They're going to be like more forces, right? Exerting on the container wall, right? And therefore, the pressure has to increase. The number of moles of the gas is obviously increasing, right? Because we're adding gases. And in terms of the average distance between the molecules, that has to go down because it says the volume is constant, but now we have more people, like more moles of the gas, so they're going to have a smaller space between themselves. Okay, I hope that makes sense. Thank you everybody for watching this video. There are going to be a lot more coming up on this chapter. Stay tuned for that. Take care of yourself and bye-bye for now.